So now how do we query the suffix tree? We saw how to query the suffix trie, and we know the suffix tree is related, but let's talk very specifically about how we would query the suffix tree and how expensive these queries are. Okay, so we saw with the suffix trie that if there's one really basic query that the suffix trie is good at helping us to answer, it's a substring query. So how do we check whether a particular string S is a substring of the text T, given that we have this data structure which has organized all the suffixes of the text in a particular way? And the answer is, we're going to do something much like we did with the suffix trie. We're going to walk down from the root according to the characters of S, right? Usual thing, walk down. However, with the suffix tree, there's the complication, not a very big one, but a key one, which is that as we go to walk along the suffix tree, sometimes we are walking from node to node, but sometimes we are walking along an edge, right? Because the edges now can have labels that are strings, not just characters, right? So, let's just look at a few examples. Let's say our query is ABA. So if we're going to walk down this tree, suffix tree, according to the characters ABA, we're going to proceed kind of in 3 steps here. One, and this is a sort of normal node-to-node movement, just like with the suffix trie, very, very familiar. Then the next character in our query is B, but that causes us to move on to this edge here, but not all the way along the edge, right? We've only matched the first B on that edge, so we're like standing here now in the middle of the edge. And then the next character from the query is A, and that moves us the rest of the way along the edge, so that this is the whole journey we took, and it took us to here. Right? So that first query, we would walk down from the root. The first step would cause us to walk from the root to another node. Second step causes us to walk along an edge a little ways. And then the third step causes us to walk the rest of the way across the edge. And at no point do we fall off, so the answer is yes. Okay. So just a slight change to how we did things with the suffix trie. Let's look at another example, BAA. So let's walk down the root according to the characters BAA. Well, first, from the root, we walk along this edge, but again, we walk sort of part way along because we've just matched that first B. The next character is A. Okay, that matches the next character on my edge label, so I'll walk the rest of the way along the edge to this node. Then last character in my query is an A, so I walk part way along this edge whose label starts with A, and that's where I stop. Okay, so I didn't fall off, so the answer is still yes, but it's kind of interesting that in this case, our walk ended in the middle of an edge, right? We didn't actually end our walk on a node. So this is in contrast to the suffix trie, where every step of every walk you were on a node. With a suffix tree, sometimes you're not on a node, you're on an edge. You're like part way across an edge. Okay? And here's another query string, ABB. Let's see what happens here. So let's start at the root. We go down according to A. Okay, great. That takes us here. Go down according to B. Okay, great. That takes us partway across this edge because we matched that B. And now the next character is a B, and we fall off. So the answer is no. But, interestingly, we fell off, again, while in the middle of an edge. Right? So we don't necessarily, when we fall off, we don't necessarily fall off at a node. We might fall off in the middle of an edge. Okay, but you get the idea, I think, right? It's much like what we were doing with the suffix trie, except here, because we've coalesced these suffix trie edge labels into string labels, there's kind of 2 different ways to walk, to take one step down the tree. You either walk into a new node or you just walk along an edge. Okay? So let's bring back the question. We asked the same question about the suffix trie query. What's the time required to match a query string of length n? Okay, well, we know exactly what we're going to do. We're going to do this walk down procedure from the root as always. And it's only a little bit more complicated now than it was before because we have these two different ways that we might proceed. We might advance only along an edge, or we might advance into a new node. So for example, when we matched ABA, the first step, the first A, caused us to move across an edge to a new node. The second step, B, caused us to move just part way along an edge, and then the third one caused us to move the rest of the way across the edge. And I'll say that this is very similar to what we were doing with the suffix trie, this new complication of these two different ways of taking a step don't really make the algorithm any more complicated. Either you're doing a lookup to figure out which edge to walk along, just like we were with the suffix try, which we already said it's reasonable to assume is constant time, or you're walking along an edge, in which case all you're doing is a character comparison to see if the next character from your query matches the next character in the edge label. I'm going to say that's also a constant time operation. And so just like with the suffix try, this query overall is big O of n time. Okay, here's another query that we saw with respect to the suffix try, which was how do we count the number of times a query string occurs as a substring of t. So you might recall that this actually sort of had two components to it, because the first thing we would do is we would walk down according to the characters of S, then we would count the leaves in the subtree below where our walk ended. So for example, if our query was ABA, the first thing we'll do is we'll walk down according to ABA. That takes us to here. The next thing we'll have to do is look at that subtree, the subtree rooted at the spot where our walk down finished, and ask how many leaves are in that subtree, and in this case the answer is 2. Okay? Very, very, very much the same thing as we were doing with the suffix try. If our query is just B, then what will happen? Well, we'll walk down according to B, which means we'll just walk partway along this edge and we'll sort of end kind of in the middle of that edge. That's okay. We can still think of the subtree rooted there, right? The subtree rooted where our walk ended. Equivalently, you can think of it as the subtree rooted at the destination of the edge that you stopped in the middle of. But either way, we can see what subtree we're talking about. We're talking about this subtree here, right? And there are 2 leaves, so we know the answer to that query is 2. Let's say the query is just A. That causes us to go here. We're looking at this subtree. In this case, there are 4 leaves, so the answer would be 4. Very much the same thing we were doing with the suffix try. We're just doing the equivalent thing now with the suffix tree. Okay, so we know we can do it. It's right there in the shape of the suffix data structure. The answer is in the shape of the suffix data structure. Okay, and it's got these 2 components. First, we walk down according to the characters of our query. Then we count the leaves below. So now let's ask a question that we did not ask before with respect to the suffix try. Let's ask, how much work is that? What's the time required for this algorithm? Okay? And we can think of this separately for the 2 parts. The walking down according to S, all right? The walking down according to S, that part we already know because we just said this for the presence-absence query that it's big O of n time, right? By our usual walk down argument. So no problem. But what about that second part? The part where we have to count the leaves in the subtree rooted at the end of our walk. This is a little bit more complex, okay? Because we need to figure out how long it takes to do that traversal, and that, in turn, requires us to understand how large the subtree is. But we can actually figure that out. Okay, let's see how we can figure that out. So first of all, let's define a variable, k, where k is the answer, right? K is the number of leaves in the subtree rooted at the end of our walk down, right? So if that's k, then can we characterize the size of the subtree that we have to traverse in terms of k? What is the size of the subtree we have to traverse in terms of k? And the answer is that we can reuse the same sort of argument we used to argue that the overall suffix tree is big O of m nodes here, to argue that that subtree is big O of k nodes. Okay? So that subtree, but that has k leaves, the total number of nodes in that subtree, it just consists of the leaves and the non-leaves, and we can use the same no only child principle that we used before to argue that if the number of leaves is k, or m, then the number of non-leaves has to be at most k minus 1, or m minus 1. So here we're going to argue that the number of non-leaves in the subtree is at most k minus 1, and therefore the overall number of nodes in the subtree is big O of k. So if you're using a traversal, like a depth-first traversal or something like that, the amount of actual effort you have to expend to traverse a subtree with big O of k nodes is big O of k time, right? It's just going to be constant work per node to do your traversal. So that actually answers the second part of the question, right? So the first part of the time bound was how long does it take to walk down according to the characters of S? That's big O of n, constant work per step. How much work is it to traverse the subtree rooted at the end of that walk? Well, that's big O of k, where k is the number of leaves. In other words, k is the answer to our query, right? So if we're going to do one and then the other, then we could say that the overall time that we need is the sum of the two. So we would say that the overall time required to both walk down according to S and count the leaves below where we ended our walk is big O of n plus k. Okay? So to answer that count query, we need big O of n plus k time. Well, if we're counting, another thing we could do instead of just counting is reporting. We could actually report where are the places where all these substrings occurred. That's just a matter of reporting the number that we find in the leaf. Right? So when we traverse the subtree rooted at the end of our walk down and we encounter a leaf, instead of just incrementing a counter, we would actually report what's the offset in that leaf. Okay? So let's bring back the fact that the leaves of the suffix tree are actually annotated with the offsets of the suffixes. That we said we said this when we were first discussing the suffix tree, and say, okay, well then, if we want to actually report where those substrings occur, where the occurrences of S are within T, then we can do our walk down according to S and then report the offsets that we find in the leaves. So, for example, if we walk down according to A, B, A, and look in the subtree, we'll get 0 and 3 as the answer to our query. And remember, the text T is ABA, ABA, $. So yes, the two occurrences of ABA occur at offsets 0 and 3, right? We can just visually confirm that pretty easily. Okay, if the query is B, then we walk down sort of here, partway along this edge, and again, we traverse the subtree rooted there. We find these two leaves, so we give the answer 1 and 4, and that is indeed where the two occurrences of B are in the string. Likewise, if we get just A, we're going to report those leaves, 2, 0, 3, 5. And so you can see it's totally equivalent to what we were just doing when we were counting the number of occurrences, except we are just additionally reporting them. We're just reporting the offsets where those occurrences occur, where they are within T. So how much work is this? It's the same, right? We're doing the same amount of work to report those occurrences as we were to count the number of occurrences. We still have to walk down from the root. We still have to traverse the subtree. It's exactly the same sort of work. It's just slightly different in terms of what it is we're doing when we actually reach a leaf. Okay, so the amount of time required to solve this problem, which is basically the exact matching problem, right? The amount of time required to solve this problem is big O of n plus k, where n is the length of the query and k is the number of places where it occurs. So to sum up all of these basic queries that we saw, how much time is required to answer the question, does P occur, when we query the suffix tree? That's just big O of n, where n is the length of P. Big O of n. How much time does it take to count k occurrences of the pattern P within the string T? Well, that's just big O of n plus k. Big O of n, the n part is because we have to do the walk down. The k part is because we have to traverse the subtree. How long does it take to report the k places where P occurs within T? Same. It's exactly the same procedure. It's just we're doing something different when we reach the leaves. And how much space is required? Just big O of m. The amount of space required for the suffix tree hasn't changed, right? That's still big O of m. Now take note, especially of this line here, because reporting k occurrences of P in big O of n plus k time is good. I just want to point this out, right? Notice that we're basically solving the exact matching problem where we're taking a string of length n and matching it against a longer string of length m and reporting all the places where it occurs, and we're doing that in big O of n plus k time. It seems hard to do much better than that. After all, we have to at least look at the query string and each of its characters in order to solve the exact matching problem. So it's hard to imagine that n wouldn't be in there somewhere, right? The n has to be there. The k, if we assume that it takes some effort to report each of those offsets, to actually report them back to the person who presented the query, then it makes sense that k has to be in there too. So having it take big O of n plus k time is about as well as we could expect to do. And notice m is not in there. M is not in that time requirement for this query of reporting the k occurrences of p within t. That's very notable because the fact that we can solve the exact matching problem, finding all the offsets where a pattern p occurs within t, and we can do it in an amount of time that doesn't even depend on m, the length of the text t, speaks to some of the power of the suffix tree.